Hey everyone, welcome to second semester, the first lesson. You'll notice that I am in like dad clothes. I got my dad hat and my dad shirt on. That's because all my cameras and all my microphones and everything are at school, and I forgot that I have to make this lesson before the beginning of the semester actually starts. So I would beg your forgiveness in my appearance, but otherwise, let's go ahead and get started. This whole semester is going to be focused on, or at least the third quarter is going to be focused on the idea of the integral. And we'll talk more about that as we progress throughout the semester. But before we get into an integral, we have to understand some basic concepts about area. And so remember I told you that calculus brings in every aspect of math, every type of math that you've done in the past is going to be brought back here. And specifically in this case, we're going to be talking about area, areas of a rectangle, areas of a triangle, areas of a trapezoid, areas of circles. But you might have seen this in pre-calculus or analysis, the idea of rectangular approximations, okay? So our goal today is to be able to explain the difference between a right hand, a left hand, and a midpoint approximation. And we'll get more technical in terms of that as we move forward in future lessons. But right now we just want to be able to calculate those things and understand the difference between those three things, okay? But before we do that, remember this equation way back from, I don't know, 7th or 8th grade, this equation of distance equals rate times time. Now, this equation is built on the assumption that the rate is constant, right? We can figure out how far we travel if we know the rate at which we're traveling and how long we're traveling for, as long as that rate is a constant. At least that's what you've been told throughout your experience in math thus far. You're going to find that that equation actually holds very true when the rate is not a constant either, okay? So here's an example. If a car travels at a constant rate of 60 miles per hour, how far did it travel from 1 p.m. to 4 p.m.? Now, obviously, you should know the answer to this. We know that we have distance equals rate times time. Duh, the distance is going to be equal to the rate, which is 60 miles per hour, times the time, and the time is from 1 to 4, so that means we have a 3-hour time period. So we're just saying 60 times 3, which is 180 miles. Now, let's go through the units of this. This might help you. Distance equals rate times time. Thinking about units here, distance is going to be miles, and the rate is going to be in miles per hour, and then the time is going to be in hours. And so you can see that the units work in terms of the algebra. The hours are going to cancel out, they're going to reduce, and you're left with miles equals miles. So when I take the rate times the time, we get miles per hour times hours, which reduces to miles there, okay? So that is going to be our foundation. Distance equals rate times time. Now, this hopefully will blow your mind here in a second, okay? Because we're going to look at this through a graphical approach. The key word in this particular problem is that the rate is a constant, okay? Well, what kind of function is a constant? A constant is a horizontal line if we were to graph that on an XY coordinate plane, okay? So we have a function, and we're saying that v of t is equal to 60. The rate is equal to 60, velocity is equal to 60. Now, velocity also implies direction. We'll talk about direction and having a negative velocity in the future and all that. But the bottom line is, if I'm traveling at 60 miles per hour, my velocity is 60. My speed is 60. My velocity, I guess, could be negative 60. Now, if I'm going to graph this on a velocity time graph, we're going to have a constant function, just horizontal line. How do I get 180 miles out of this? Well, from 1 o'clock to 4 o'clock, we're saying start at 1 and end at 4. And notice what do we have here? We have a rectangle. And how do I find the distance? Well, I multiply the rate, and in this case, the rate is the height, and the time is the width of that rectangle. So the distance equals rate times time equation is equivalent to the area of a rectangle where the rate is the height and the time is the base. Base times height, area is base times height. So right there, your mind should just be blown that we can relate the idea of geometry to the idea of rate and distance, okay? So again, we find the area under that function, and the area under that function, or the shape, is going to be a rectangle. So the distance the car traveled is equivalent to the area of the rectangle that we just drew, okay? Now, this is true even if the function, even if the velocity is not a constant. The idea is this. If velocity, in our case, velocity was equal to 60, but let's just say velocity is variable. Let's say velocity is equal to sine of t plus 1. Well, sine of t plus 1 is going to look something like this, right? And if we go from 1 to 3, we would be looking at from 1 to 3, because, let's see, that's pi there, so 1 to 3 would be more like that, okay? We would be finding the area bounded from 1 to 3, we'd be finding the area under that curve, essentially. You go, well, how does that make sense? We don't have a rectangle there. It's true that we don't have a rectangle, but the idea, the principle is still there. We can find the distance that was traveled by figuring out the area underneath the curve, bounded by the curve, the x-axis, and the time intervals. Okay, so that's kind of a cool thing. The big question then becomes, how do I find the area of that shape? Because it's not a rectangle, and that's where calculus is going to come in. Okay, so let's go ahead and look at the next thing and see how we can approximate this area. We can't find the exact area, but we can approximate it. And so we're going to look at this funky shape that I have drawn here. How would I find the area of that piece? If you remember back to some of your basic geometry principles, we can approximate, we can estimate that area by cutting it into pieces. So for example, I could cut it into a rectangle, actually two rectangles. Okay, how could we estimate that area? We would cut it into rectangles. Now the reason I cut it the way that I did is because you can see I have a little bit that's above, a little bit that's more than the actual area, and then the second rectangle, the 3x4 rectangle, is a little bit smaller. So hopefully those will kind of compensate for each other. But the idea is that we're just approximating here. We're not looking for the exact areas, okay? So here we have the approximation for this shape would be 5 times 3, and then 4 times 3, and then add those up. Or be consistent, base times height, which is 3 times 5, plus base times height, which is 4 times 3. So we'd end up with 15 plus 12, or 27. Again, this is just an approximation. So how is it that I could get a better approximation? Well, the answer to that, how can I get a better approximation, would be just cut it into more rectangles. Cut them into smaller rectangles. And here's the key. The more slices that I have, the smaller the slices become, right? So the more that I have, the smaller they get. But when I add them up, the more accurate I get. And you can see when I do this, in this particular case here, myself some slack. Well, let's see how do I do this. We can see that if I cut it into rectangles that are only one unit wide, and that's why I'm using graph paper here, because I got 3 boxes and 4 boxes. Well, if I cut it into rectangles that are only one unit wide, right? We have this amount that's too much, a little bit more that's too much, a little bit more, and now we have too little, and too little, and too little, and too little. But the bottom line is I'm going to get more accurate because all this extra space that was up here that I was adding before isn't there anymore. Same thing on this side. So this first one would be 1 times 4. The second one would be 1 times 2, 4, 4, and 4.7-ish, right? 1 times 4. And then 1 times like 4.6, 4.7. And then 1 times 5, because the height is 5 there. And then 1 times 4 again. 1 times 4.6, or sorry, 3.6, 3.7. And then 1 times 3.2. And then 1 times 3. And then when I go and add those up, multiply all that out and add it up, I get 27.5. So pretty close to the original approximation, but it's going to be a little bit more accurate because I cut it into more rectangles. So again, that makes us ask, how do I find the exact area between the curves, or how do I find the exact area of that region? Well, here comes the calculus. To find the exact area, you would take the limit. Well, the limit of what? You would take the limit of the sum of the areas as the number of rectangles approaches infinity. So we would say, I have this shape, whatever the shape is. Let's say I've got a shape that looks like this, and I'm trying to find the area underneath it. Well, I can cut it into 2 rectangles and find those areas, or I can cut it into 4 rectangles, or I can cut it into 8 rectangles, or I can keep cutting it into an infinitely thin rectangles, but as I get thinner and thinner and thinner, there becomes more and more and more of them. And then when I add up those very small areas, I end up with a very accurate, in fact, exact area under the curve, because we're taking the limits. We're saying that limit is approaching the exact area. So if it's approaching a specific value, that is going to be the exact area. We'll talk more about that in future lessons, but that's just kind of a glimpse of where we're going, okay? So let's go ahead and take a look at a non-constant function and come up with an approximation of the distance that was traveled, okay? So here it says a particle starting at the origin, and that's going to be key. We're starting at the origin, which means the position of the particle is 0 when t equals 0. Okay, that's our initial condition, if you remember that term from before. We know that the velocity is t squared, so we have v of t equals t squared, and we're looking for time at when time is greater than or equal to 0. We're looking for the position of the particle when t equals 3. So that means if we're starting at t equals 0 and we're going to t equals 3, that means our width, or our time interval, is going to be 3 units. So if I go ahead and graph it, and I'm going to put the original one, the 60 miles per hour one, right? This was the constant, and we were finding the area under the curve from 1 to 3, we're finding that area. We could say from 0 to 3 if we wanted to make it match this, right? So we're finding the area of this whole thing if we go from 0 to 3, and therefore our distance would be equal to our rate times our time, which in this case would be 180. Now, in our case, this is a velocity time graph. Just like this is going to be a velocity time graph, t squared looks something like that. And we are looking for the position of the particle. Now notice this looks different than this, the distance traveled. The 180 is the distance traveled. Well, if I start at my initial position, x of 0 is 0, I started at the origin, I said, then my position is going to be whatever my distance traveled is, because I would just add my distance traveled to my initial position. We'll talk more about that later. There's a difference between displacement and position. But our displacement, you would say, is 180. We would add that to our initial position to find out where we actually are. And because our initial position is 0, then our position will just be 0 plus whatever our distance traveled was. Now, if we're looking from 1 to 3, so let's say, from 0 to 3, we're going to find the area under that curve. Again, we don't know how to do that exactly, but we can approximate it using rectangular approximations. So it depends on how many rectangles I want you to cut it into, and it'll usually say in the problem, using 3 subintervals that are equal in width or something like that, okay? So in this case, in my case here, I'm using 3 subintervals, and I'm cutting it from 0 to 1, from 1 to 2, and from 2 to 3. And you'll notice that, where did I get my heights from? Well, this is 1, this is 2. So those are my pieces that I'm cutting into. I've got to find the area of those pieces. Well, what is the height of this rectangle? That's going to depend on, maybe I should use the middle one. That's going to depend on which height or which value of this function do I use. Do I use v of 1 or do I use v of 2 to determine the height of this piece here, okay? Well, if I use v of 1, if I use this height, that's v of 1, I would be finding this area, just this rectangle, okay? If I use v of 2, I would be finding the area of this big rectangle here. And well, how do you know which one to use? You don't want to be inconsistent. You want to either use a right hand or a left hand approximation. So the one that I used was a right hand approximation, because out of these two, the way that this rectangle is drawn right now, which height did I use? Well, I used the height when t equals 2, which means I used the one out of the two options that I had, I used the one on the right to determine the height of this rectangle. Now I still have to find the area of this piece, so do I want to use the left point or the right point? Well, if I'm going to be consistent, I'm going to use the right point. So I'm going to find the area of that one. So I'm using v of 1 for the first height, v of 2 for the second height, and then I'll use v of 3 for the third height. I'm going to tell you right now, this is where I got lost in calculus when I was in high school. The left and right hand, which one's left, which one's right, okay? Looking at the graph, we are using, in this case, a right hand subinterval, or right hand approximations, because in each rectangle, I'm using the value on the right, not the value on the left. So v of 0 or 1, well, I'm using the 1 to determine the height. 1 or 2, I'm using the 2. 2 or 3, I'm using the 3. So I'm using a right hand subinterval. So what I'm going to do is I'm going to figure out these heights. Well, v of 1 is 1, because I'm plugging that in here, 1 squared. So v of 1 is 1. V of 2 is 4, and v of 3 is 9. So if I want my right hand approximation, is going to be, what's the width? Well, the width is going to be 1 times the height is 1, plus what's the width here? The width isn't 2. The width is how big this second rectangle is. How far is it from 1 to 2? It is 1 unit. How tall is this rectangle? Well, this rectangle is 4 units tall. Now the last one, how wide is that? Well, the distance from 2 to 3 is 1 again, and the height is going to be 9. And so when I add those up and I simplify it, I've got 1 plus 4 plus 9, which is 14, okay? So we would say that the distance that we traveled is approximately, and that's important, approximately 14. Because we started at position 0, and we add to it the distance that we traveled of 14, then my position is going to be 14, 0 plus 14, okay? So that is using 3 subintervals that are a right-hand approximation. It's x of 3, x of 2, v of 3, v of 2, and v of 1 were our heights. X of 3, or the position when t equals 3, is 1 times 1, 1 times 4, and 1 times 9, all added up, which gives you, again, 14. Now, if I wanted, let's see here, if I got rid of that and I wanted to get more accurate, how do I get more accurate? Well, I get more accurate by cutting it into smaller rectangles. And you can see here that what I did was, instead of looking at 3 subintervals, I looked at 6 subintervals. Well, if I look at 6 subintervals that are all equal in width, how wide is each subinterval? And this is where it can be very tedious to do the work in your head. Your calculator is going to be a benefit for these kind of problems. If you get something where it's like 100 subintervals or 1,000 subintervals, you can find a program by Googling Riemann sum calculator, and you'll find plenty of options to use for those kind of things if you need it. But still, we're looking for the area under the curve from 0 to 3. Well, when I cut it into 3 subintervals, that was pretty inaccurate. So what I'm going to do instead is cut it into 6 subintervals. And I'm going to get closer to what my actual value is. Well, how do I figure out the width of each subinterval? Simple. You take the end point, the end time, subtract your initial time. So it was from 0 to 3 was our time interval. If it was from 1 to 3, we would say 3 minus 1. And then we would divide that by how many subintervals I have. And that's pretty simple to see that if I have 3 wide and I'm cutting it into 6 subintervals, then each subinterval will be 1/2 unit wide. But that's a good formula. It's the ending time minus the initial time divided by how many subintervals. That's going to tell you how wide each subinterval is if they're equal subintervals. Now we need to figure out, since we're doing a right hand here again, we need to figure out the height of each one of these intervals. So from 0 to 0.5, from 0.5 to 1, to 1 to 1.5, from 1.5 to 2, from 2 to 2.5, and from 2.5 to 3. Those are my 6 subintervals. For the first one, well, would I use the time 0 or the time 0.5 to figure out my height? I would use the time 0.5. So I'm going to figure out what v of 0.5 is, and I'm going to multiply that by 0.5. Okay, that's going to be the area of that first rectangle. The second rectangle, we'll add to that, is 0.5 wide again, times, well, what's the height? Am I going to use the 0.5 or the 1 to figure this height out? I'm going to use the 1 because I'm doing a right hand. I'm using the right hand 1. Am I using the 0.5 or the 1? The 1 on the right, the 1. So we're going to use v of 1. Okay, and then the third one is going to be 0.5 times the 1 on the right, between 1 and 1.5, that would be 1.5, so it would be v of 1.5 plus 0.5 again, because they're all 0.5 in our case, times, the next one is going to be v of 2 plus dot, 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 dot. We should have, when we're done, we should have 6 area, or rectangles, 6 rectangles areas. So there's one of them, there's 2, 3, 4, I'm missing 2 of them. The next one will be 0.5 times v of 2.5 plus 0.5 times v of 3. That would finish out the 6 subintervals, okay? So we would say that our position would be those areas added up. Now notice it says use a table to determine the value. So you would type this maybe into your y list, v of t equals t squared into your y list, and then you would set your table to start at 0 and have intervals of 0.5, and it'll give you those velocity values, and you can just plug them in right there. So v of 0.5, let's see, I got it here. v of 0.5 is 0.25 because 0.5 squared is 0.25. v of 1 is 1 squared, that's 1, that's easy. v of 1.5 times 1.5 is 2.25. v of 2, that's 2 squared is 4. v of 2.5, well, 2.5 times 2.5 is 6.25. And the last one, v of 3, is 9, because 3 squared is 9. So we go ahead and simplify all of that, and we end up with 11.375. And so it kind of makes sense that when I had 3 subintervals here, and I only cut it into, I have my function, I only cut it into 3 subintervals, you can see that there's all this extra space that we're counting that we really shouldn't be counting. So that's why we cut it into smaller pieces. So you can see all this extra space here is being eliminated as we make the rectangle smaller and smaller and smaller. Okay, so that means that this approximation is going to be less than this approximation, and it's getting closer to the actual value. So it does make sense that our original approximation using 3 subintervals was 14, and our approximation here was 11.375. So we're quite a bit closer. Now you could, and we'll talk about this as well, you could do a left-hand Riemann sum, okay? If I do a left-hand Riemann sum, just looking at 3 subintervals here, if I do a left-hand Riemann sum, well, from 0 to 1, this one gets a little weird. From 0 to 1, which height should I be using? I should be using the one on the left. Well, the height of this guy is 0. V of 0 is 0 squared is 0, so we have a rectangle that's 1 wide by 0 tall, right? We're talking theoretically here, we don't really have a rectangle, but that's what we would have. And then for the second rectangle, between 1 and 2, we would use the one on the left, so we'd use v of 1. And then between 2 and 3, we'd use v of 2, because that's on the left as well. And so we'd be finding the area, and you can see that the approximation that I'm coming up with is now below the actual area of the curve, or area under the curve. And so this is going to be an under approximation, where this one's an over approximation. Now you can't really say, well, I'll just find these two and then find the middle of them and that's the exact value. That's not going to work because there's some concavity here. So there's actually more space that is over approximation than less space that's being under approximation, if that makes sense. Okay. All right, let's go ahead and look at, oops, going a little too far here. Let's go ahead and look at, oh, there we go. A practice that I would like you to do. Now, this is the same function over the same time interval, but I want you to approach it using 12 subintervals, using a left hand, a right hand, and a midpoint approximation. You go, well, what's a midpoint approximation? Go ahead and pause it, see what you come up with, and then when you get stuck or you think you have an answer, come back, push play, and then you'll compare to what I got here, okay? All right, so with that, let's see what my answers are here are. For the 12 subintervals, I got 10.15625. For the left hand, I got 7.90625, and that makes sense. The right hand should be above the actual value, and the left hand should be below the actual value just based on how we draw it. And in the midpoint, I got 8.984375. We go, how did you get those? I mean, I tried, but I didn't get it. Well, let's kind of go over them and see what we got here. If I'm looking at 12 subintervals, and we're going from 3 to 0, so for 12 subintervals, how wide is each subinterval going to be? The width of each subinterval is going to be 3 minus 0, the ending time minus the starting time, over how many subintervals you have. So what is the total width? The total width is from 0 to 3, so it's 3. And then we're cutting that into 12 subintervals, so we're dividing that by 12. 3 minus 0 over 12 is going to be 1/4, or 0.25. So the width of each one of these subintervals is going to be 0.25. Whether I'm using a left hand, a right hand, or a midpoint, the width is 0.25. And so I will set up my table using my calculator somehow. V of t was, oops, not x, t squared. So I'm finding my velocity values at these points. So we're going to start at 0 and move 0.25, then 0.5, 0.75, 1, 1.25, 1.5, 1.75, 2, 2.25, 2.5, 2.75, and 3. Now we can figure out all these values. I'm going to kind of skip over some of them here, just because I don't know them, to be honest with you. This one was 6.25, this was 2.25, this was 0.25. And I don't know what those are. 0.25 squared, 0.75 squared, 1.2, and so on. Okay, you can figure those out. I'm just going to call this V of 0.25, V of 0.75. And the reason I'm doing this is because I don't have my calculator with me. So, like I said, I left everything at school over Christmas break thinking I could get a break. And then I realized I had work to do. So anyways, so those are the values now. If I want to use a right hand with 12 subintervals, I would say that it's approximately, well, the width of the first one is going to be 0.25 times the height of the first one. Well, I want to use the right hand value. So which one's on the right? Is the 0 or the 0.25 on the right? The 0.25 is on the right, so we're going to use that value. So we're going to use V of 0.25. And then plus the width of the second subinterval is from 0.25 to 0.5, so it's 0.25 again. And then times the right hand value. The right hand out of these two is 0.5, so we're going to multiply that by 0.25, or V of 0.5, right? V of 0.5. And then plus dot, 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 dot. We'll go down to the last subinterval, and if you want to see this using 12 subintervals, this is a good way of seeing it. I'll do a little box here. There's my rectangle. There's my next rectangle, my next one, and so on. And you can see these rectangles being formed here. We should have 12 subintervals. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we'll skip down to the last few here to make sure we're using the right values, okay? The width of the last two. Well, the width is always 0.25, so we'll use the interval from 2.5 to 2.75. So we'd say times the value at 2.75, because that's to the right. Out of these two, that one's to the right. So that'd be V of 2.75. And then plus the last one, 0.25, the width, times the height. The height is going to be determined by the right-hand value. So it's going to be 9, or V of 3. The key that you need to make sure, and I don't have enough room on this whiteboard to write this all out, is that when you are summing these up, you have to have 12 rectangles. A lot of times students will have 13 rectangles because they're trying to use every one of these t values in their approximations, and you don't want to do that. You want to use the value that's determined by, in this case, the right-hand value. So that is your right hand, and so that would be 10.15625. Okay, so that's your right hand. Your left hand is going to look very similar, but we want to use left-hand values. Well, the width is always going to be 0.25, but if I want the left-hand value, I'm going to use the one. Which one's to the left, the 0 or the 0.25? The 0 is. So V of 0 is 0, plus 0.25 times the next subintervals from 0.25 to 0.5. So which one's on the left? The left-hand one is the first one. So it's V of 0.25. V of 0.25 plus 0.25 times between 0.5 and 0.75. The one on the left is going to be the V of 0.5, so 0.25. And then plus dot, 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 dot. And then we'll use the last one. So the width is 0.25. And then the left-hand subinterval, the left-hand value is going to be using between 2.5 and 2.75. We're going to use a 2.5. So times 6.25. And then plus 0.25 times the one on the left would be V of 2.75. And again, you want to make sure that you have 12 rectangles here, okay? And that approximation was 7.90625. Okay? So those are the left and the right approximations. The midpoint, when you're doing 12 subintervals using a midpoint, it gets really gross. And that is because midpoint. The subintervals are still 0.25 wide, okay? But 0.25, 0.25. Okay, so again, you need 12 subintervals and they all look the same. The widths are all 0.25. But if I want to find the midpoint values, this is not the midpoint values. This is the left and the right. The left and the right, the left and the right. We need to find the middle of those. So what we want to do is we want to find the value in between 0 and 0.25. So we would actually find the velocity of 0.125, the one that's between these two. The one that's between these two is going to be V of 0.375, I believe. The one in between 0.5 and 0.75 is V of 0.625. And then down here, between 2.5 and 2.75, that's going to be V of 2.625. And then between 2.75 and 3, that's going to be V of 2.875, I believe. I believe that's what it is, okay? So midpoint gets kind of gross, especially when you have a lot of subintervals. Normally, like on the AP exam, it won't give you so many subintervals and it'll give you a nice clean table to work with on this, okay? All right, we have the actual area under the curve. The actual distance traveled, or the position in this case, is 9. The area under that parabola is 9. We'll talk about how to do that analytically in the future, but it's very important that we know how to do rectangular approximations. Let's go ahead and take a look at one more example here. I want you guys to try and do this on your own. And the table in this case is set up a little bit different, and it might make it easier to see. So you can work with it here. This eraser is not very good. All right, for this last one, notice in the table I gave you time and I gave you velocity, but instead of time and velocity, I'm giving you time and velocity. Most of the time, tables are written like this. And the reason they're written like this is because we can see the right and the left-hand subintervals very easily in this case. So we've got time and we've got velocity. From, let's see, 0, 60, 120, 180, 240, 300, 360, and 24, 30, 28, 30, 26, 24, 26. This is why tabular methods are so important, because sometimes we don't have functions to work with, we only have sets of data. Now in this question it says the table above shows the velocity of a particle in feet per second at 7 different points in time. 1, 2, 3, 4, 5, 6, 7. So how many subintervals do I have here? Well, I have the one between here and here, between here and here, here and here, here and here, here and here, here and here. So I've got 6 subintervals, if you would. It says estimate the distance the particle travels using a left hand, a right hand, and a midpoint rectangular approximation with 3 subintervals. So if I want 3 subintervals, we got to figure out how wide each one is. So if we're starting at t equals 0 and ending at t equals 360, we'd say 360 minus 0 over 3 subintervals. So each subinterval is 120 seconds wide. So here's what I like to do. I like to say, okay, here's my first rectangle. From 0 to 120. The next one is from 120 to 240. And the next one is from 240 to 360. That way I can see the rectangles. There's 1 rectangle, 2 rectangles, 3 rectangles. So for the first one we want is a left-hand subinterval. So left hand. And notice we're doing 3 subintervals. So we would say it's approximately, how wide is the first one? From 0 to 120, it's 120. The second one from 120 to 240 is 120. And the third one from 240 to 360 is 120. Each subinterval is 120 wide. Now we need to figure out the height of these rectangles. Because I'm looking at the left-hand value, from 0 to 120, what is the height on the left-hand side? Well, would I use the 0 or the 120? I would use the 0 because that's on the left. So the height is 24. From the interval 120 to 240, the one on the left out of these two is the 120, so I'm going to use the height there, which is 28. And then from 240 to 360, the one on the left is 240, so I'm going to use a 26. So that is your approximation for left hand. For right hand, each subinterval is the same, so it's 120 times something, plus 120 times something, plus 120 times something. But this case, we're using the right hand. So from 0 to 120, the right hand is the 120, so that height is 28. From 120 to 240, the right hand value is 240, so we're going to use the 26. And then from 240 to 360, the right hand is the 360, so we're going to use the 26 there. And so you can see that even though the widths are the same, the heights are all different. For the midpoint approximation, there's still 120 wide. So we have 3 subintervals that are each 120 wide, okay? And they're not always going to be the same. In this case they are. They're equal subintervals, but these might be unequal. So we have to figure out the distance between those by subtracting them. But they are all 120. Now for midpoint, well, between 0 and 120, I don't want to use the left. I don't want to use the right. I want to use the one that's in the middle, in between 0 and 120. Well, 60 is right in the middle. So what's the height at 60? That's going to be 30. Then from 120 to 240, don't want to use left, don't want to use right. I want to use the one in the middle. So I want to use the 180, which is 30. And then from 240 to 360, don't want to use a 240, don't want to use a 360, I want to use the one right in the middle, which is 300. So the height at 300 is 24. So again, the width, remember, to find the area of each rectangle, this is the width, how wide it is from time to time, 120, and then the height is determined by the function's value, the velocity value down here, okay? And then you simplify that and you get your approximation. So if we simplify all of those, we get those answers there, the 9,360, 9,600, and 10,080. All right, I hope that this lesson was beneficial to you. Again, forgive me for my attire, but I think that we got through a very important lesson. And in the next few videos, you're actually going to be hearing some interactions with students in the classroom from days past. So with that said, have a great night. If you have any questions, please comment below or reach out to me through tutoring or some other way. I'll talk to you all later.